Welcome. In this video I'm going to talk a little bit about the Hayes Chronograph. So most people who are vintage computer enthusiasts are probably familiar with the Hayes Smart Modem. This is one here. These date from the 80s, maybe the 90s. This is actually a 14.4, so it's probably a little bit on the newer side. Back in the early days you'd get these in probably 1200 baud or so, maybe even 300 baud. Anyway, I always thought it was kind of an iconic look to these things. You had this aluminum case, top and bottom, the black in between here, the front panel with the red bezel with the lights behind it. On the back, of course, you've got a real DB25. So what most people probably don't realize is that Hayes also made a real-time clock. Back in the day, computers didn't come with real-time clocks. You would have to, on your IBM 5150 for example, you'd turn it on, you'd have to type in the date and time. The IBM and clones pretty quickly ended up with multi-function cards that would include battery backed up clocks. But if you really go to the early period, to the, when the IBM 5150 first debuted, or even before that with some of like the Atari computers and such, they didn't have a clock. There wasn't necessarily an easy way to add on a clock. So Hayes figured they'd come out with a separate clock, and they put it in the same sort of form factor as their modem. Now here's a picture of the clock. I don't actually own one. I kind of wish I did, but these things have always eluded me. You can see it's a little bit taller than the standard Hayes modem, and it has a beautiful VFD vacuum fluorescent display in the front of it. So I finally gave up searching for one of these and just decided to build my own. And this is the result. So I've kind of tried to duplicate the form factor and the features. It does have a vacuum fluorescent display. That's not an LCD, that's an actual real VFD. And of course it does have an actual DB25 out the back. So let's take a little bit of a closer look at this clock project. So I have zoomed in a little bit so you can see the vacuum fluorescent display in the front of the clock. I actually used a Russian IV28B display in this. This was sort of the most appropriate display I could find. I wanted something that had 7 segments rather than graphic, and I wanted something that was relatively small, would fit in here, and I wanted to get something that was not an intelligent module. So typically in my projects I've used Noritake displays. They're like $50, a 2-line by 20 character serial. This is actually just a display, and we'll get a look at it in a bit, and I'll show the schematic of how I interface to it. But it's just the raw display that you have to drive with your own driver logic and your own high voltage supply. I did add a couple buttons to the front so that you can switch modes on the display. So here is a mode on the timer that includes a 10th digit. Ever since the Heathkit, world's most accurate clock, it's always felt to me like the way to demonstrate that you have a better clock than average is to include that tenths of a second digit. That just kind of says to the world, hey, look at my clock, it's special. I also gave it a blank mode. I gave it a date mode, so 2020, July 11th, today's date. And then there's the time mode. So the real Hayes Chronograph had a slightly better display than mine. It had something that did have the days of the week, Monday, Tuesday, Wednesday, Thursday, etc. across the top of the display. I just could not find one like that. So if you search long and hard enough, you might be able to find a display like that that had the days of the week and was set up more for a clock. Maybe something from an old VCR. I've seen a few pictures of projects that look like they're old VCR clocks. But you can't really find them in quantity. You can only you get lucky, you find one of them and it'll be expensive. So I went with this IV28B, which was dirt cheap. Thinking like $10 for 10 of them, like $1 a display. That's what I used. And then of course the back of it, I've got power going in, plus the DB25. So let's start by talking a little bit about the vacuum fluorescent display module. So if it looks kind of like that, you've got a bunch of digits. Each one of these digits is going to have a grid that's going to come out the bottom, and we'll call that digit, I don't know, numbering doesn't matter. Let's start over here. We'll just start with 1 on this side. And 3 3-digit N. So each one of these digits has a grid, and each digit is comprised of 7 segments. So we could call this one A, B, C, D, E, F, G. I'm not sure I got the letters in the right order, but you get the idea. You've given these digits numbers, you've given these segments letters, and then there will be a filament F0, F1, a filament that runs across the display. So how do you drive your VFD display? Well, what you do is you take and you supply, first you start by turning on the filament. That's just a heater type element. You put one side of the filament to ground, and you put the other side to 5 volts. And you actually want to put a little resistor in there to current limit it. So put an R. If you really wanted to do this right, you would drive the filament with AC. For a small display and simplicity, you could just drive the filament with DC. As your display gets bigger, you'd end up with problems where one side of the display got brighter than the other if you try to use DC. But on a tiny little IV28B, just use DC. It's so much simpler than using AC or using DC and pulsing it back and forth or some crazy thing. Just go for simplicity. So the filament, you've got to have that always energized whenever you want the display on. Your next task is to light your particular digits. Now you're going to have to multiplex them. You can't light them all at once, but you'll do this one, this one, this one, on, and then that one. And then you'll repeat the sequence. You do this sequence fast enough, human eye will not be able to tell that you're multiplexing. So let's say we want to turn on, let's say we want to put a 2 on this digit. So what we would take digit 2 and we'll put 30 volts on that pin. And then we will light up the appropriate segments that comprise a 2. So all of these segments, 30 volts. If we do that, then that 2 will light up on there. And then we take and we turn it off, we blank it for, just a fraction of a second. We go and we put the 30 volts on this one and we display what segments we want on it. So it's just a process of continually multiplexing that display. People familiar with doing multiplexing on LED displays probably find that quite similar. The one thing that makes a VFD really unique is that you need this 30 volts or so. It varies by the display, but this is a relatively high voltage to be dealing with for most people are used to digital electronics. So hopefully that gives you a little bit of background on how to drive a VFD. There are videos on the web that will give you a lot better overview than I've given here on it. So let's take a look at our actual clock schematic. So starting here, we have the VFD. And just like I explained, it's got a bunch of anodes here for the segments, and it's got a bunch of grids for the digits. So you put your 30 volts here, and your 30 volts on the right section of those, you get your digit displayed in the right spot. We also have the filament comes down here. I broke it out into a header so that I can reverse the polarity if I wanted to. I don't think it makes a difference. I put a resistor on there and to limit the current, and it's ground and 5 volts. So that's connecting the VFD. Now, next question is, how are we going to drive this 30 volts to each of these pins? So what we're going to do there, rather than implementing a bunch of transistors ourselves, we will use a VFD controller. This is a Max 6921. It's a fairly dumb chip. It's not smart like it would do the multiplexing itself or something like that. It's a lot like a plain ordinary dumb shift register. You shift in a bunch of bits via its clock and data and load pin. So there'll be a C, a D, and a load. You shift in those bits, and those bits will turn on various drivers here on the output. So what you will do is you will shift in a bunch of bits that turns on your grid and your anode that will display your digit. Then you'll shift in some bits that will blanket and then you'll shift in bits for your next digit, and you'll just repeat that over and over again forever, and that will keep that display displayed. Over here we have a Pi 0W, just a standard Pi 0W. There's not a lot going on here. I did put protection resistors on some of the I/O lines. Sometimes I do that in my projects when I'm working on diagnosing the software and designing things, and the idea there is just to prevent the case where you've accidentally misconfigured a pin as an output and connected it to another output, for example on a GPS or something, and now you've got a situation where two devices could be trying to put out conflicting signals and you could short one of them and damage it. So I put those current protection resistors in for safety while prototyping. In production, those will just either be taken out or just wired across. In here, we've got several different GPS headers. GPS modules, you can get them from AliExpress, from Banggood, from eBay. There's different ones with different pinouts. The original one that I liked, it became unavailable. Switched to other ones, so most of my clock related projects will have several footprints. And these GPS will be serial. It'll have a receive and a transmit. You want those going into the UART on the Pi. Got some headers over here that let you configure how the UARTs are connected. So you got your receive and transmit for the GPS, and you've got a pulse per second. The pulse per second you can use to get very, very precise synchronization, so plumb that line through. Over here we have a Dallas. So I wanted to preserve the ability to do this as kind of a dumb non-GPS clock. If you really wanted to simulate the way a Hayes chronograph worked back in the day, it obviously wouldn't have a GPS. It would just be a battery-backed clock. So there's a footprint here for a Dallas real-time clock chip. Who really wants to do that when you can use a GPS and have it all automated and synchronized? I don't know, but we had room on the board, so I left this, and it's unpopulated. Over here, we have the high voltage supply. This is a standard boost converter. You'll see a few places I put in multiple footprints, like there's multiple footprints for the inductor. It's really just one inductor. But basically a boost converter, you've got an inductor, you've got a switch, in this case a transistor, and you've got a diode right there, and you've got a storage capacitor. So that's your typical boost converter. Now, the boost converter chip I usually use to drive my high voltage supplies was 12 volts, so I needed something 5 volts. So what I did is I just used an AT Tiny 85. I mean, mostly what you've just got to do is output a pulse width modulated signal. So you can do that with an AT Tiny 85 just fine. I put a potentiometer here for set point so that we can set this to a particular point with the pot. The AT Tiny 85 will compare the set point on the pot with the voltage on a sense resistor, and it will adjust the PWM up or down to produce your 30 volts coming out here. 30 volts comes out here, goes into the VFD controller, goes into the VFD to light your digits. Then over here we've got your serial drivers. So to drive your real DB25 connector, you need serial drivers so that it can do the right kind of voltage and current out on the serial port. So I used a pair of Max 3232 chips. Now that is a 3.3 volt serial driver, perfect for interfacing with the Pi. One driver is usually sufficient, but looking at the Hayes Chronograph schematic, they plumb through all kinds of additional lines on the DB25, like the carrier detect is there, like the ring line. The ring is actually used to signal when an alarm goes off. So I wanted to be able to do the full feature set if I want to. So I plumbed all of these DB25 lines that comprise a standard serial port through. So here is the PC board for the chronograph. It's all assembled. You can see we have a Raspberry Pi over here piggybacked on top. So it's somewhat of an unfortunate way it ended up put on here. I wasn't thinking I put the SD card right behind the display. Next revision, we'll see if we can flip that around a little bit. Pulling the Pi off. You can see that I used a stacking header on it so I can plug it in through the bottom. Might be more convenient to mount it upside down. That would flip the orientation of the SD card and allow you to avoid having to use a stacking header, so I'll consider that change. Looking at this here, you've got the two drivers for the RS-232. These are Max 3232 chips. One of them handles transmit and receive in a couple control lines. The other handles another 4 control lines. We have most of the lines plumbed through to the DB25. We have the unpopulated socket here for a Dallas real-time clock, as well as an unpopulated spot for a crystal, and a header here where you could hook up a battery. No real plans to use that, but if you wanted to be a purist and not use the GPS, you could do that and actually have a ticking battery backed up clock. Here we have the GPS module. This is something I got off of Banggood that was very, very cheap. It lacks a PPS pin. I'm going to switch to a GPS module that does have PPS pin for the next time I build this. Down here is the high voltage supply, so we've got a potentiometer for the set point. The AT-Tiny 85 is the controller. Here's the transistor for switching, an inductor, a diode, and a couple capacitors. You'll notice the capacitors are tiny. We just really don't need a whole lot of high voltage to drive this display. Here we have the VFD controller. It's the one surface mount chip that had to go on this board. And here we have a resistor kind of hacked in here onto a header, and this is the filament resistor for the display. So when I made this original revision of the board, I forgot to put filament resistor in, so that kind of had to be hacked in afterward. And then of course on the front here is the VFD display and a couple buttons. I am doing a revision of this board. You can probably tell the schematic doesn't quite match the board. You can see some hacks I placed on this original version to change it around. So one of the mistakes I made with my original design was the assignment of the UARTs on the Pi to the peripherals. I hooked up this DB25 to the primary UART and the GPS to the secondary. That turns out to be really inconvenient because there are daemons already pre-built for synchronizing the GPS, and they want it on a physical UART, not connected to a PI-GPIO software UART. So most of this hacking you see down here was to flip the UARTs around. The schematic that I showed in this video is already consistent with the plan changes for the UARTs, with moving the Pi, a bunch of stuff like that. Okay, given that the whole purpose of this Hayes chronograph is to serve as a time source for a computer, it seems only fitting that we try it out over the serial interface to see what the protocol looked like. I have attempted to at least somewhat reproduce what I think the serial protocol looked like. Given the manual, I hope I've got it at least close to being right. I have set a couple options in my terminal program. Let's see right here. You can see I've turned on a local echo, and I have translated carriage returns to carriage return line feed. So if we do a typical AT command, we will get a response. The 8 is actually a syntax error in that AT by itself isn't a valid command, but a couple of these are valid. So like AT-DT will tell it to display the time. So if you were actually looking at the hardware itself, you would see that it just started displaying the time. AT-DD will tell it to display the date. I realize you can't see this on the screen capture, but the hardware on the VFD just started displaying the date. A few of the other things we can do ATRD will read the current date. So there you go. It's 2020, July 11th, and ATRT will read the current time. It is 2:30 and 23 seconds. There are some commands to set delimiters inside the string. So if we do ATVT colon, that should set the separator in the time string to a colon. ATVD, let's try slash. That should set the date separator to a slash. And ATRD, now we have slashes in there. ATRT, now we have colons in the time. There's also a command that turns line feeds on and off. So if I do an ATLS, I should get an extra line feed. I already have my terminal translating carriage return to carriage return line feed. So now we'll get carriage return line feed. We'll get like an extra blank line. Can turn that back off. There is a command to set the time, ATST
120000P. This isn't actually going to set the time because I have the whole thing synced to the GPS and I'm not allowing it to override the GPS, but this should put it into AM PM mode. Oops. Let me try that again. ATST 120000P. Like I said, it's not going to set the time, but the P will cause it to go into 12-hour mode. There we go. So now ATRT 23220P. There's also a command to return the day of the week in ATRW 6. Today is a Saturday, so it is the 6th day of the week. There is also a set of commands for doing the alarm, so you can actually set an alarm and it'll send a ring signal to the computer. I have not implemented the alarm command. So anyway, that's kind of it. So if you wanted to interface with this thing, you would boot it up and you would do an ATRD, an ATRT, and you would have your current date and time, and you could configure the clock in your computer to that date and time.
Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.